Hey everyone, I'm Anton Call. Welcome to Math 143. I wish we could be together in person, but obviously we can't. So let's make the best of it and let's just get straight to the math. So what we're going to study for the first half of this class is series and sequences. So we're going to start with a definition. A sequence is an ordered list of real numbers. Typically, we'll write it out like this. So our sequence will go like this. A sub 1, that's the first of the numbers. A sub 2 is the second. A sub 3, and so on. For the most part, we'll be interested in sequences which are lists of numbers that go on forever. So to indicate that it goes on forever, I'll just put a little ... here. Each of these numbers is called a term of the sequence. So A sub I is the ith term of the sequence. Now, sometimes I'll write the sequence out as a list like this. Sometimes I will indicate it slightly differently. So we often indicate or denote sequences as with little curly brackets, and then I would put an A sub n, where n equals k to infinity, or sometimes just curly brackets around A sub n. So when I write this, what I'm saying here is I'm thinking about a sequence whose terms are A sub, and this bottom right here, it starts n equals k, so it would be A sub k, then A sub k plus 1, A sub k plus 2, and so on. So if I want to specify the sequence using this notation right here, I will typically, if it matters, I'm going to indicate who the starting point is. And you'll see I'll do examples of this in just a minute. So if the starting point is important, then I'm going to write n equals k at the bottom, indicate that it goes on to infinity. Sometimes I just want to refer to the sequence more generically, where I don't need to worry about the starting point, and so I won't write the little subscript here or the superscript. Right? So sometimes I will write out some terms of the sequence. Sometimes I will use this notation, and we should be able to sort of comfortably be able to go back and forth between the two. So so say it like this. So specific sequences may be indicated by listing a few terms. Now, typically then what I would do is I would list enough terms so that everybody can see what the pattern is, so they can figure out who the rest of the terms are. So indicated by listing a few terms, or by formula. And that's the situation where I often will use this notation right here, the curly bracket notation. So for example, right, so here's a sequence, 1, comma, 1/2, comma, 1/3, comma, 1/4, ... Now I think everyone can figure out who this sequence is, or who the next terms are going to be. So what do we have here? We have a list of fractions, right? If you think of 1 as 1 over 1, a list of fractions whose numerator is 1 and whose denominator is increasing by 1 as we go. Right? So I can write it in this form right here, right, as a list, or I could write it as, so let's see now, who are these? These are sequences of the form 1 over n, where n goes from 1 to infinity. Right? So either of these indicates the same sequence. Right? And we should be able to comfortably be able to go back and forth between the two. So here's an example. So let's write the following sequence, n over n plus 1, where n goes from 1 to infinity as a list. So in this example, we've been given the sequence in formula style, right? And we need to convert this to list format. And so how does this go? Well, let's see, when n equals 1, we'll have the fraction 1 over 2. When n equals 2, we'll have the fraction 2 over 3. And so I think you can see what's happening here, right? Both the numerator and denominator increase by 1 as we go. And the difference between the two, right? The numerator is always going to be 1 less than the denominator. So 3/4, 4/5. That's probably enough terms so that everybody can see what the pattern is. Here's another example. So in our previous example, we started off in formula style and we had to convert to list style. Now I want to go the opposite direction. So let's find a formula for the following sequence, and the sequence is going to go like this: 1, 2/3, 4/9, 8 over 27, I'll give you one more, 16 over 81, ... Okay, so what you should notice, right, from this sequence right here, let's see, every numerator is a power of 2. Every denominator is a power of 3. And so what we have are fractions that are powers of 2/3. And so the answer here is going to be this. It'll be 2/3 raised to the n, where, remember, 1 is when n equals 0, right? 2/3 of the 0 is 1. And so this would be starting point n equals 0 goes to infinity. All right, so there's the formula format for this sequence right here. Another example. So same thing, let's find a formula for the sequence that goes like this: 1, comma, minus 1, 1, comma, minus 1, 1, comma, minus 1, going on forever. Right, so what do we have? Our sequence just alternates 1, minus 1, 1, minus 1, 1, minus 1. And so hopefully everybody can see that the way to accomplish this by formula is to take powers of minus 1, right? When n is even, we will get positive 1. When n is odd, we'll get negative 1. So this would be sum n equals 0 to, or sequence minus 1 to the n, where n goes from 0 to infinity. Here's an example of a famous sequence. In fact, it's got a name, so this is called the Fibonacci sequence. Fibonacci sequence. And this sequence is famous for a number of reasons. I mean, it gets studied quite a bit. It has various nice properties. In particular, it helps model certain natural phenomena. Certain phenomena in nature can be described using this sequence right here. And the way this sequence goes, instead of using a sub 1 and a sub 2, I'm going to use f for Fibonacci. So f sub 1 is equal to 1. F sub 2 is equal to 1. And then for a subscript that is greater than 2, right? So when n equals greater or is greater than or equal to 3, it works like this: f sub n is equal to f sub n minus 1 plus f sub n minus 2 if n is greater than or equal to 3. Or I should say when n is greater than or equal to 3. So what does this sequence tell us? Well, it gives us the formula. And how does this formula work? F sub n is obtained by adding the previous one and the one that was 2 before. All right? So to get it started, then we need to tell you who the first 2 are, and then the formula kicks in and it says add the previous 2. Right? That's what this formula says. So how does the Fibonacci sequence work if I was going to write it down as a list? 1, 1. Okay, now add the previous 2. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 13, add the previous 2, that'll give you 21, and so on. Right, so there's a more complicated sequence in terms of formulas, but in the end, it's actually easy to compute additional terms, right? Just add the previous 2. Now, our concern is going to be what happens to the terms of the sequence as n gets larger and larger. So we want to study how the sequence behaves as we get larger or go farther and farther down the line. Right? So we want to say, or try to characterize what the behavior of a sequence is going to be. And so here's a definition. The sequence A sub n converges to L if A sub n can be made arbitrarily close to L by taking n sufficiently large. Okay, so that's kind of a mouthful. What is it saying? It's saying that the terms, the A sub n's, can be made as close as you like. When we say arbitrarily close, what we mean is as close as you like, closer and closer and closer, by choosing n large enough. All right? So if the terms are getting closer and closer to this particular number L, right, then we say that it converges to L. And in this case, so in this case, we write, and this definition should look familiar to you, or it should sort of remind you of the definition of limit as of a function as x goes to infinity. It's almost the same definition. So in this case, we write that the limit as n goes to infinity of A sub n is equal to L. Otherwise, so if this does not occur, we say that the sequence, sorry, I'm kind of running out of room here, the sequence A sub n diverges, right? So when you have a sequence, there are two choices, right? It either converges or diverges. In the case that it converges, what we're saying, or when we say that it converges, what we mean is that the terms of the sequence are approaching one particular number. They're getting closer and closer to that number. If it diverges, then some behavior, some other behavior is happening, but it's not getting close, not approaching one particular number. Right? So notice we use the same notation, this limit notation, right, that you learned in Calc 1. Right? And so this is going to be one of the main things that we do in this class is we study limits of sequences, right? It's going to come up for the first half of this class. It's going to come up every single day. We'll be asking our question, what's the limit of a particular sequence? So let's look at some examples now. So first, let's look at the sequence 1 over n. Well, as n goes to infinity, what's happening to this fraction right here? Well, the fraction has a constant numerator 1, right? But the denominator is getting larger and larger and larger, which means that the fraction is getting smaller and smaller. So the sequence 1 over n converges to 0. Right? And we write limit as n goes to infinity of 1 over n equals 0. Let's look at some more examples. How about this one? Limit as n goes to infinity of cosine of n times pi, right? So there's a sequence cosine n pi. Now think about, for various choices of n, if n is an even number, right? So I'll have like cosine of 2 pi, 4 pi, 6 pi, and so on. When n is even, cosine of n pi is equal to positive 1. If n is odd, cosine of n pi is negative 1. So what is this sequence, what are the terms of this sequence doing? They're going plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. They are not approaching one particular number. Right? And so this limit does not exist. I typically use DNE, I write DNE to indicate that the limit does not exist. All right? It's not approaching one particular term, so this sequence right here is divergent. Another example, how about limit as n goes to infinity of 2 to the n. So let's think now, if you take 2 and raise it to ascending powers, 2 to the first, 2 squared, 2 cubed, 2 to the fourth, and so on, those numbers are getting larger and larger and larger. Right? And so in this case, I would write that this limit is equal to infinity. Once again, what we have is divergence, right? The limit is the output of the terms of the sequence are not approaching one particular number, right? And so it's divergent. So what we have here, here's an example of a convergent sequence. Both of these are divergent. And notice, I mean, here I wrote does not exist, here I wrote infinity, right? Both of those are correspond to divergence, but they diverge in two different ways, right? Here, the numbers are blowing up, right? They're getting larger and larger and larger, where in this case, they're bouncing back and forth between a couple of different numbers, right? So I wrote does not exist, I wrote infinity here, both correspond to divergence, but we're sort of letting the reader know in which way they diverge. Now, I've kind of talked my way through convergence and divergence for these examples right here. All right, but we want to be a little bit more systematic when it comes to analyzing sequences. And here's the idea, as I mentioned, this definition of convergence and divergence of sequences is very close to one that you learned when you were studying functions back in Calc 1. And so that's what we want to do, is actually use our knowledge of functions to analyze the limits of sequences. All right, so we can use our knowledge of functions to analyze sequences. And here's how it goes. I'm going to write this as a theorem. So we're going to start out with a sequence. So let's say, given the sequence a sub n, suppose that we have a function, so f of x satisfies the following property. F of n, every time we plug an integer in, we get a sub n. Right? So f of x is a function, which means that we're allowed to plug in numbers that are not necessarily integers, right? F of 1/2 and f of pi, and so non-integers. But suppose that this function has the property that whenever you plug an integer in, 1, 2, 3, 4, 5, and so on, the output is exactly the same as the terms of the sequence. All right, so suppose that we have this situation. Now, if the limit as x goes to infinity of f of x equals some number L, then the limit as n goes to infinity of a sub n is equal to L also. Okay, so if we have a function whose behavior when we plug in integers matches the behavior of the sequence, then we can compute the limit of the function, and if we get the number L, then we know exactly the same limit it holds, or the same result holds for the limit of the sequence. Now, there should be no reason, there's nothing mysterious going on here. This function has a name, it's called the associated function. There's nothing secret or nothing surprising here. So this function, so the function, f of x called the associated function is obtained. From the sequence a sub n by replacing n with x. So there's nothing earth-shattering going on here. You've got this sequence, it's got a formula that involves n, just replace the n's with x's. And then what this theorem says is you can use all the techniques that you learned for computing limits of functions, right, to analyze the limits of sequences. So what are these techniques? And I guess I should let me say that. So this allows us to use techniques for computing the limits of functions to analyze sequences. Now, what do I mean when I say techniques for limits of sequences, or techniques for computing limits of functions? For example, and probably the most powerful one of those is L'Hopital's rule, right? So you can use L'Hopital's rule. There's the squeeze theorem. Etc. Anything that you know about computing limits of functions will now apply in this setting, right? Okay, so let's do a few examples of that. Let's say that our sequence looks like this. So let's say determine whether the sequence 3n squared over 4n squared plus n plus 1, where n goes from 1 to infinity, converges or diverges. Okay, so what do? We want to find the answer here. What we want to do is look at the associated function and compute the limit as x goes to infinity. The associated function is found by just replacing these n's with x's, and so we're going to compute the limit as x goes to infinity of 3x squared over 4x squared plus x plus 1. If you want now, so I mean, this is a situation where you could use L'Hopital's rule, but you don't have to in this setting, right? When you have polynomial over polynomial, where the degrees match, you can compute the limit. You can write the answer down, right? You look at the fraction of leading coefficients, and so what we get here is 3/4. And so what does that tell us? Right, so our conclusion is that the sequence 3n squared over 4n squared plus n plus 1 converges. And we can be specific in this case, it converges to the number 3/4. All right, so that's how this associated function business works, right? We're given a sequence, compute the limit of the associated function. If you get an answer, then the original sequence converges to that sum number. If the associated function diverges, then you say that the sequence diverges. Now let's do one more example, and then we're going to need a little bit more power before we can move on to more complicated sequences. Now this one, what I want to do is I want to compute the limit as n goes to infinity of 1 plus 1 over n raised to the n. All right, so what we want to do is we're going to replace that with the associated function. So I want to compute the limit as x goes to infinity of 1 plus 1 over x raised to the x. All right? Now, when I look at this one right here, as x goes to infinity, inside the parentheses, what do we have? Well, 1 over x is approaching 0. So we have 1 plus 1 over x. Okay, so inside the parentheses, we've got 1. As an exponent, we have infinity. And so this is indeterminate of type 1 to the infinity. Don't write equals 1 to the infinity, and especially don't write 1. Right? What you want to do is remember from Math 142, in the situation that we have a 1 to the infinity, that's an indeterminate form, which means that we need to analyze it further. How do we analyze it further? Well, one thing that you should remember, when you have an exponent that's causing trouble, right, natural log helps us deal with that exponent. And so here's the idea. I'm going to write y equals 1 plus 1 over x raised to the x, and then I'm going to take the natural log of both sides. So natural log of y is equal to natural log of 1 plus 1 over x raised to the x. And why does logs help us deal with exponents that are causing trouble? Because there's a rule of logs that says we can bring that exponent out front. So we have x natural log 1 plus 1 over x. Hopefully this is looking familiar from Math 142. All right, but I'll go all the way through on this one. And this is really one that you may already know the answer. This is one that's going to come up quite a bit in this class, so you should just know who this one is. All right, so now what I want to do is I want to compute the limit as x goes to infinity of this piece here, so that'll be an x times natural log 1 plus 1 over x. All right, as x goes to infinity, we have this part going to infinity. Inside the parentheses is approaching 1. Natural log of 1 is 0. So the indeterminate form now is infinity times 0. Hopefully remember what you do. You can't just use L'Hopital's rule yet, but this is an indeterminate form which you can manipulate and eventually apply L'Hopital's rule. So this is limit natural log 1 plus 1 over x, and then I'm going to divide by the reciprocal of x, so we get this fraction here, and this is the indeterminate form 0 over 0, right? The top is approaching 0, the bottom is approaching 0, and so we have a 0 over 0. That is a situation where you can now apply L'Hopital's rule. And so whenever I apply L'Hopital's rule, and we'll use L'Hopital's rule all the time in this class, that's why you learned it in 142, because we're going to need it all the time in 143. Whenever I use L'Hopital's rule, I put a little LH over the equal sign to indicate to the reader that I'm now using L'Hopital's rule. So what I need to do is take the derivative of the top, take the derivative of the bottom separately. The derivative in the top is going to be a negative 1 over x squared divided by 1 plus 1 over x. The derivative of the bottom will be a negative 1 over x squared. All right, so here's the derivative of the top, here's the derivative of the bottom. And now let's simplify things a little bit. In fact, these negative 1 over x squareds are going to cancel, right? And so what we're left with is limit as x goes to infinity of 1 over 1 plus 1 over x. Now, as x goes to infinity, well, let's see, the numerator stays at 1. The denominator is also approaching 1. And so that limit's equal to 1. Now, notice, what did we do? We did not, the answer here is not equal to 1. What we showed is that the natural log of y is approaching 1. To undo that, we need to exponentiate. And so what we get is that, so conclusion, right? When I exponentiate, what we have is limit as n goes to infinity of 1 plus 1 over n raised to the n is equal to e to the 1, which is equal to e. Right? So this is a well-known fact that we're going to need, right? So this is one that you should essentially memorize. You should definitely know how to compute it. The limit as n goes to infinity of 1 plus 1 over n raised to the n. That's equal to e. Right? Okay, so I was just checking the time there. It looks like we're at about half an hour. Now, typically the lectures will be somewhere between 30 and 45 minutes. I don't usually, I mean, occasionally maybe we'll make it to an hour. Since this is our first lecture, I'm going to stop here. I'm going to pick up with a second half. That will be the next lecture to watch. And so I'm not going to assign homework. I'm going to call this one Lecture 1A. The next lecture you look at will be Lecture 1B. Once you finish Lecture 1B, you'll be able to do all the homework. So I'll assign the homework with the next one, okay? So let's just keep it a little bit light, and I'll finish things up with another lecture that'll be ready to watch for tomorrow. Okay, so have a good day, and I'll see you next time.